So hello everyone, this is an extension of the previous Dataloader video. In this video we're going to take a custom dataset, right, which is not part of the datasets library. It is something that we downloaded from the internet as an open source, and we're going to load it using a Dataloader. We're going to write our own custom dataset Dataloader class and load it, because this is something very important. Whenever you guys train a deep learning model, you'll be doing it on some dataset which is not part of the PyTorch library. It will be something custom, right, your own dataset. So understanding how to use the data loaders in order to load your own dataset is very essential. So this video is gonna be amazing.
Hello everyone, welcome to another video in this series of using PyTorch to train deep learning models. In this video we're going to watch how we can take a bunch of images and convert them into a PyTorch compatible dataset and then use it to train a image classifier. And in this video we'll be using the Stanford dogs dataset, which consists of around 120 dog breeds, and we'll be using it to train a deep learning based image classifier. And I'll walk you through the entire pipeline of loading the images from the disk, creating the dataset, the data loader, and then finally training a deep learning model to get a pretty robust classifier. So let's get on with it, guys. So as you can see, I have all the necessary libraries important here. We also have a few libraries related to image loading, such as image from the PIL library, and also a few functions such as train, test, split from sklearn, which will allow us to split the dataset into the necessary val, train and test splits. Let's go ahead and check the data now. So as you can see, in the data folder I have my Stanford dogs folder as well, and inside the images is where all the images lie. First, let's go ahead and put down our root folder. Root folder is where my code resides along with all the data points. So in this case, the root folder is basically PyTorch series folder, which is part of the home folder. So now in this dataset, in the Stanford datasets, we have one images folder, and in that folder we have all the images under various subdirectories, which I'll show you just in a minute. So the idea is that we'll write a particular class, and that class would actually help us to split it equally, like with an equal distribution into val, test and train. So as you saw in the images folder, there were multiple subfolders, hub, docs, breed, right? So the idea is to write this dataset splitter, which is a class, and this dataset splitter would take in the images root directory and then split it into the necessary train, test and val splits, which will be used during our training time. So in the init function, in the initialization function, what I'm doing is I'm mentioning the data path. The data path is the path to all the images which are present, and we'll be loading all the images from this data path itself, right? So I'm initializing an empty list, which is list of images, and this image list is supposed to contain all the images with their absolute paths. I'm using the glob library in order to do so. The glob library basically can find patterns in a particular path which is given to it. So in this case, I'm taking os.path.join data path. Data path is essentially the path to the Stanford dogs folder, and then I'm using star for all the subfolders inside it, and then .jpg for all the JPG files basically. So this will actually load all the image files, right? Cool. So I've declared a dataset splitter object, which is basically the dataset splitter class, and instantiated it. Now we're gonna just go ahead and print all the images that are present inside list of images. We'll take a bunch of them and see if we did get the absolute paths from the folders, right? So we'll just go ahead and print out list of images. There you go. So the first 10 images in the list, these are absolute paths to the images in the subdirectory Silky Terrier. So this list of images basically contains all the JPEG images in the Stanford dataset. Cool. So what I'm going to do is actually create a data frame out of this dataset. So data frames are very convenient in order to structure data points out. So basically the idea is, first we'll have a dictionary, and this dictionary will contain two fields basically. So the first field is, or the first key is image paths. So image paths is going to be a list, and this list would contain all the images, and the labels list inside this data dictionary is going to contain all the labels, right? So that is the idea, and then we'll convert this dictionary into a data frame. The data frame would be a structured table of all the images, the dog images and their corresponding labels, and then we will use the same data frame and split it out proportionally into all the splits that we talked about, which is train, val and test. Cool. Now the idea is to iterate through all the images which are present inside self.list of images, and we'll try to get the label from the absolute path itself, and we'll also append the path of the image into the image list, which is part of the dictionary, right? So now, as you can see over here, we have the image path, and the label is actually part of the image itself. So in this case it's silky terrier, and in order to extract it, we'll have to split the image using the separator, which in this case is /, and then we'll use some further split commands on it. So we'll just go ahead and split it up, and we'll use image file.split, and inside that we'll pass the delimiter, which is going to be os.path.sep, which is in fact /, and as you can see, it provides us with a list of all the individual tokens in the path. And then if we do a -2, we get the second last index from this list, and then we're gonna split it again using a hyphen, and that's gonna give us silky area. So this is a pattern that I have actually observed in all the images which are present. So it's an ID followed by a hyphen and followed by the label which is present. Yep, so there you go. So what I'm gonna do right now is take this label and we're gonna append it into self.data.dict labels, right? And we're gonna do the same for the image path as well. We're gonna append the image path into self.data.dict image paths. So we have a dictionary. So this loop is actually going to run over all the images which are present inside self.list of images, and we're going to append the image path along with the label into the lists contained in a dictionary. Now if we call pd.dataframe, pd is just pandas, which we had imported in the beginning of the video. So if you just call pd.dataframe on a dictionary containing keys, it will automatically create a data frame with the columns as the key names, right? So we'll have a data frame with 2 columns, and the first column would be image paths, and the second column would be labels. So yeah, so let's go ahead and check it out. Actually, let's see if we are actually getting the data frame or not. So before that, we'll actually have to call the self.prepare dataset function in the initializer itself. And now, as you can see, if I do a data splitter.datadf.head, I get the data df, which is the data frame that we wanted. We also have an index column which we would want to drop. The first column apparently is the index, and we're doing one more thing. We are actually taking the data frame and we are shuffling it up. So that when we do create the 3 splits, right, the val, test and train split, we don't have any bias. Like, we don't want any particular label to be part of a split and we missed out in another split. So the idea is to shuffle it initially so that we don't run into such issues later. So we want an equally distributed data set when we do those splits. So here I'm just taking a sample and I'm keeping the fraction as well. So when I do a dot sample fraction is equal to 1, it will actually just return me the entire data set, and which is but shuffled, right? So randomly selecting rows from the data frame, and I've set the random state as well, and I do a reset index. So the resetting the index will actually again line up all the rows from 0 itself, and then we just drop the extra index column which was present initially, right? Because when I do a reset index, it will actually add a new column, so I want to remove the previous column which was there, and now we have our shuffled data set containing labels as well as images. So the next step would be to encode the labels. In our data frame, as you can see, all the labels for the dogs are in the string format, so this won't be consumed by the deep learning algorithm when we train it. So it has to be converted into some integer format, some numerical format, right? And we'll be using the label encoder module, which is part of sklearn library for this. The label encoder can actually convert a list of strings into a list of integers. So when we call label encoder.fit on the list of strings, right, it would actually create a mapping to another list of integers, and this can be used to have a unified set of integers for our labels. So if you go inside the fit function, you can see that it accepts an array like input, which can be array or a list, and there are some examples here itself. So we can do so here they are doing a le.fit and pushing the list of cities, and which in turn gives out a list of integers. So yep, so we'll be doing the same for our case as well. Here we are doing a label encoder.fit, and we are calling it on the labels series of the data frame. So in order to convert the labels series to a list, we are doing a toList on it, and then we are adding a new column to the data frame called converted labels, and we'll apply the label transformer function on the labels column, and this would actually create a new column called converted labels containing the mapped integers. So yeah, so that's how it's gonna work. Let's go ahead and check it out. And so we're calling .transform on row on labels over here. Now let's create the instance of the data splitter class again, and as you can see, when I do a dot head, we have the converted labels column, which contains the integer values of every string label value which we had initially. Let's go ahead and create a length function, which is underscore length underscore, and this function would allow us to get the length of the entire data set that we have. It's just we just call a len of self.list of images, and when we do a len of dataset splitter, it should actually give us the length of the data set that we have. So in our case, it would be the length of the image list, and that would give us the total number of images. So we have around 20,580 images, and yep. Next up, we're gonna add the main utility of this class, which is a splitter, right? So you're gonna create a split function, and this function is going to help us split the data set equally into the 3 splits that we want, and the train, test, and val split. So we go ahead and name our function as split dataset, and in this function, first is to define the ratio of the split. So in our case, we're going to keep the test and the val ratio as 0.2. We're going to keep it same just for convenience, and then the next step would be to first split the data set into the train and test split, and for that we're using the train test split module, which is part of the sklearn library again. And this function is very simple. It just takes an array. We can pass an array into it, and we can just pass the ratio that we want, and it will automatically split it equally into that particular ratio that we have given, right? So in our case, since the train had around, so the entire data set has around like 20,000, so we do a 0.2 split. So train will have around 16,000 images, and test would have around 4,000 images, and then we'll split it again into test and val. So here we are passing the entire data set, which is data df, and the test size is going to be the test ratio that we have. So let's go ahead and put that in, and random state we are keeping it as 42 because that was the same number that we used when we shuffled our data frame, right? So the idea is to keep the random state consistent throughout the entire program. And then we just copy paste it. We just have the next line, which is going to enable us to split this into val and test. So we're going to pass the val ratio in test size, and then we're just going to return train, test, and val. Okay, so I guess we did a mistake over there. This is going to be val comma test and not train comma test. So yeah, this is done, and let's go ahead and check it out. So we're just gonna name 3 variables, train, val, and test, and call the dataset splitter split dataset method over it. So now let's go ahead and check the shapes that we had. So train.shape is around, as I mentioned, is going to be 80% of the entire data set, which is 16,000 images, and then we have val, which is 3,000 images, and then we have test, which is 800 images. So this is actually a good starting point to train our deep learning algorithm. We can also go ahead and check out the data frame itself. So this is our train data frame. It contains the converted labels, and we can also check the number of labels or number of images per label that we have. So as you can see, the total number is 119, and these are the counts per label, right? We can do the same for the val, and we still have number of unique labels as 119. So this ensures that when we do our train test split on the entire data frame, the number of labels remains the same. So if it was like 119, 117, that would have been an issue, but the train test split functions makes sure that we have equal number of labels and it is equally distributed in the splits, and the ratio per label is the ratio that we define, which is 80-20 or like 20% for the smaller split. So next we're gonna have to take the train, test, and val data frames that we had, and we're gonna convert it into the appropriate X and Y format, which is basically X being the input data and Y being the labels. So here we're gonna do an X train, Y train, and we're gonna index out the particular columns, which is train of images or train of image paths and train of converted labels. We're gonna repeat this for test and val as well, and we're gonna have all the 3 splits at our disposal in order to train and evaluate our deep learning model. Let's go ahead and check out what xtrain looks like. So on doing an xtrain.head, we get the data frame, which is just a list or just a series of the images that we had. And if I do a ytrain.head, it's the corresponding labels series. So we have separated them out, and these would be consumed by the training function and the model easily. We can also go ahead and check out a particular image and visualize it to see how it looks like. So let's do an xtrain.lock on the data frame itself and get the first index and see what the image looks like. And cool. Okay, I did a mistake over here. It seems like, oh my bad, I cannot do a lock. I should do an ilock. Yeah, so if I do an xtrain.ilock, it gives me the absolute path to the image, which seems to be an old English sheepdog. We can load it and check it out. We can see what it looks like as well. So if I just do an image.open on this entire path, I get this. So this is our input image, and this is what's going to go inside the model training function. The next step would be creating the data loader. The data loader is very essential when it comes to training the function, because the data loader would in fact load batches of data while training at runtime, right? So PyTorch makes it very simple to create a data loader, and it's pretty much the same for all deep learning methods that we write, or all deep learning pipelines that we create. So when I say same, it's like the structure is pretty similar. So here we do Stanford dogs. We just name the class as Stanford dogs, and we subclass it from the dataset module. And then let's go ahead and create the initializer. In the initializer, we would actually be passing the data frame itself, which is going to be our xtrain, or we name it as xdf over here. It's going to be of a data frame type, and at the same time we are also going to pass the labels data frame as well. And so the idea is that we'll take these two, and then when we call the get item or the get function, it would return a batch of input images along with their labels, right? Transform is something which is also needed, because we'll use this to convert our images or input data into an acceptable format. So you'll see later on how we use the 2 tensor transform function to convert the image into a tensor. We have also an optional positional argument, which is target transform. So target transform is generally used to transform the label into some other format. So let's say it's not an integer in some other use case, so we could actually use target transform to do that, right? We could actually use the label encoder inside target transform and call label encoder dot transform whenever we get a string value. So that's something that we can do it over here as well, but in our design we have just used it in the initial dataset splitter. So in the init function we have defined transform, target transform x and y, x and y being the xdf and the ydf, our images and converted label series. Next is the get item method, which is the most important method in this class. The get item method, which will actually take an index and return a batch of data points. So here we're doing a row which is self.x.ilog index, and this will return a row from the x data frame that we have, and its row is basically going to be an image. So we load the image first, and then we convert into an RGB type, because that's the format that we want. We don't want it to be a BGR image, because RGB is the image in the data set, and that's what we're going to test with also at the end. And then we take the label as well, and we do a self.y.ilog index. Now if we have transform, we are going to transform the image, and we're going to do the same for label as well. So if the self.transform is none, it's not going to do anything, and otherwise we're going to transform the image. And similarly we write a similar function for label as well. I should say a similar conditional for the label as well, where self.target transform is present, we convert the label to, and then we return image comma label, which is a tuple. We're converting the label to a tensor directly over here, because we know that our label is an integer. So when we do a get item on this, when we pass an index to the object or instantiated object of this class, we'll get a batch of items, and that is what we specify when we call the data loader itself. The length function would return the length of the data frame that we passed. So that's standard that we're keeping across all the dataset classes that we are creating. So quick primer on the transforms library, which is part of Torch Vision. The transforms library is very, very convenient. It actually lets us do a plethora of transformation on input data types. So here, as you can see, there's a compose function which can sequentially apply transforms to objects. So in the compose function, we're actually passing center crop. So it's gonna like crop an image at the center of size 10, which is present over here. And there's a toTensor function as well, which converts the numpy array to a tensor. And then there are a lot of other functions which are utilities and can be used for different purposes. As you can see, there are like brightness, saturation, and hue transformations which can be used. And there are some random conversions that you can do as well. You can like rotate the image and so on and so forth, right? In our case, we're just gonna convert it to a tensor, and at the same time we're gonna normalize the image as well, because we want the image pixel values to be contained within a certain range, and that would allow the deep learning model to get trained over the set of images easily. So this example that you can see on the screen, where we have transforms or normalize, we're gonna do the same for our case as well. So coming back to VS Code, we are declaring dataset train with Stanford docs, and we are passing the X train, Y train, and for transforms we're going to do a compose, and inside compose we're going to pass toTensor, and along with that we're going to pass normalize as well. We're also going to do resize, because our images are of different dimensions, and for the deep learning network there we're going to choose 224 cross 224 is the acceptable input size. So resize, toTensor, normalize. In other videos we're also going to see how we can pass augmentation values as well, but for the time being this should work, this should be enough. So the values, the 0.485 and 0.56, 456, these values, right? How do I choose them? I'll get to that in a minute. but for now let's see what the dataset train length looks like. So that's the number of images that we have, and if I do a dataset train.x.ilog0, it gives me this. So these were the images. And now if I just pass index to dataset train, it returns an image and label. So that's when the get item function kicks in and returns a tuple of image and label. I'm not able to call PLT over here because of the dimension format, because okay, it's channels first, so I'm going to use the permute function which we studied about previously in our tensor primer videos. And there you go, we have our image which is normalized, so hence the color values looks a bit different, but this is what the normalized image looks like. The next step would be to create the data loaders. Creating the data loaders is very easy. We will just create a variable called train data loader and then pass our entire data set that we have created into the data loader function. Data loader would technically take in an object of type dataset, and it would also require us to set the batch size and if we want to shuffle it. And then when we invoke data loader, it will return data points from that dataset of that particular batch size that we just defined. So in our case, we have defined batch size as 32 and 32 for both train and val data loader. Now if I just want to call data loader, I will do a next of iter on it because it's kind of a iterable. And yeah, if I print item.shape over here, you'd be able to see that it's a tensor of shape 32, which is the batch size that we created, and we have 3, 224, 2, 224. So this actually shows that there are 32 images of 3 channels and of width and height 224, 224 each. So that's 32 images together, which are gonna go inside our deep learning training function. So the batch size totally depends on the GPU that you will be using during your training, because batch size would define how fast your network would actually get trained. So in the next video, we're going to take this data loader, train data loader and val data loader, define our deep learning model and train it. Cool. So see you in the next video, guys.